Hello everyone, and welcome back to another video where we are going to be evaluating this awesome integral with some complex analysis that was solved by Maths 505. It's from a Berkeley math competition, and also saw that black pen, red pen had to go at this as well. So, thought it was about time that we also do this for funsies. Woohoo! But let's get started, shall we? The first thing we're going to do is note that this here is an even function because we have two signs. So if we were to pull out a negative from both signs, they would just cancel. So we can just rewrite this integral as being like 1/2 and then, scratch that out and just write over all real numbers. That's another way we can write it. And before we actually continue with the complex analysis thing, we need to do a couple of things with the integrand, because I don't really want to deal with signs. I'd much rather deal with e's. E's are nice. E's are fun. E's are easy. So what we're going to do is express these two signs in two different ways. We can say that sine of nx right here, well, we can just express this in terms of Euler's identity, right? We can just say this is e to the nxi, but then we can also just say it's the imaginary part of that. So let me make a little bit of space. This right here is just the imaginary part of e to the nxi. And that's just by Euler's identity. And the second thing we can say is that sine of x just on its own, well, this right here can just be equal to, I say can be, it can be equal to, no, it is just e to the xi, and then minus e to the minus xi over 2i. And by Euler's identity, I do promise you this does check out. So with this all in mind, our integral is equal to 1/2 times the integral over all real numbers of, well, the imaginary part, but I'll put the imaginary part on the outside of the integral. So the imaginary part of our integral over all real numbers of e to the xi minus e to the minus xi over 2i, and then x squared, of course, and then our sum from, let me scroll down a little bit, and then our sum from n equals 1 to infinity of e to the nxi divided by n factorial dx. That right there is the chunky boy right there, but we can deal with this integral because we can just use some complex analysis. You'll see here that our only pull is actually about the origin, and since our integral is over all real numbers, what we can just do is integrate over our indented semicircular contour. So this right here, that I sometimes affectionately call the half pizza, because it's like a half pizza, but you took an infinitely small bite out of it in the center. That really suck as a bite, because it's infinitely small, but hey, it's something. But I digress. What we have then is our line integral over the entire thing. So our integral over our entire contour is just going to be 0, because we don't actually have any poles within our contour, because you'll see we're integrating around the origin, not around. We're integrating around it over the top rather than over the bottom, so it's not actually in our contour. So this right here is just going to be equal to 0. And let me split this up into a couple of smaller line integrals right here. So we have gamma 4, I'll call this gamma 3, then I'll call this gamma 1 and gamma 2. I wrote that in order. But we have our whole line integral does equal 0, but it's also going to equal the integral over gamma 1 plus the integral over gamma 2 plus the integral over gamma 3, and can you guess what comes next? The integral over gamma 4, woohoo! But you'll see here that integrals over gamma 1 and 2, this right here is just going to be the integral we actually want, because it's just the integral over the entire real axis, because the radius of the semicircle in the origin that's surrounding the origin, that's going to 0. So in the limit, it's just going to be, it's going to approach I. The integral over gamma 4, please do take my word for it, namely by Jordan's lemma, that does just go to 0. It vanishes. But the integral over gamma 3 is slightly more interesting, and the reason for that is because we're actually integrating, as I've already said, around the origin. But not it's not like we have a point here we're integrating around it like this, counterclockwise, in which case it would just be, 2 pi I times the sum of our residue, or times the residue at that point. Instead, we're integrating over half of it in the opposite direction. So actually, rather logically, the integral over gamma 3 is just going to be minus pi I, and then times the residue at 0. And since the sum of all of these must equal 0, what we can conclude from all this is that our actual integral, so I, is just going to be equal to pi I times the residue at 0. So let's get evaluating this residue, shall we? So our actual integrand right here, and the thing we're going to be, the function we're going to be finding the residue of, is going to be the following: e to the xi minus e to the minus xi, and then divided by 2i x squared, of course, times our sum from n equals 1 to infinity of e to the n xi divided by n factorial. This right here is our function that we need to find the residue of at 0. And by the residue theorem, this really isn't too awful. I say residue theorem, by the definition of a residue, I should say. So we're going to multiply this by x squared, and then, because this is just the definition of a residue, we're going to be taking the derivative and then the limit as x approaches 0 here. So let's actually get differentiating, shall we? Because these x squareds are just going to cancel. And I'm going to throw the 1 over 2i out front because it's really not too important with differentiation, is it? So now we have our sum from n equals 1 to infinity over 1 over n factorial. But then we have the derivative of just a bunch of e's. And grouping everything together, we find that we have the derivative of e to the xi, but then plus nxi. So we can just say this is n plus 1. So n plus 1 xi, and then minus e to the n minus 1 xi. And we can just evaluate the derivatives here extremely straightforwardly because, I mean, it is just e to the something. I mean, you could do this, I guess, hypothetically in like a BC class, I suppose. Oh, that'd be fun, throwing complex numbers at them. But anyway, take the derivative of all this, we find that this is just n plus 1 times I, and then minus n minus 1 times I. And the reason we can drop the e terms is because this is the limit as x goes to 0 after all this. So the e terms is just e to the 0, and you know, e to the 0 is just 1, which is awesome. So now we're going to divide by n factorial. And we have our 1 over 2i out front, and our sum from n, I almost wrote m, n equals 1 to infinity. And you'll see a couple of things here. First off, that the i's all cancel, and also that our n's are going to cancel. And our 1 is a 1 minus negative 1, so this whole numerator we can just cross out and just write a big 2, which is going to cancel further with that 2 right there. So the only thing we're actually left with this right here is just the sum from n equals 1 to infinity of 1 over n factorial, which we just know to be e minus 1. Because the actual series for e, so I'll write this out, so e to the x is equal to the sum from k equals 0 to infinity of, well, just some x to the n, or x to the k, pardon me, x to the k over k factorial. So if we just cut off the first term, which is just going to be 1, we can re-index it to get this sum from, you know, k equals 1 to infinity, and then you just plug in k equals 0 here, you get e. Or, sorry, you get this right here, so you get e minus 1. That's basically how you do that. So let's go back and actually see what on earth we've come up with. Because we have an e minus 1 right here, and we also have a pi, so let's just kind of scroll up and see what we have. So we know that this residue right here is equal to e minus 1. So our integral is equal to pi I times e minus 1. But is I really the integral we're after? Sort of, not really. The integral we actually evaluated with this was this right here. It was, I mean, it was this inside part right here. But what we still need to do is multiply by half, and then also take the imaginary part of it. So let's just go ahead and do that, shall we? Multiplying by half, we see that this becomes, well, pi over 2 times e minus 1 times I, but what's the imaginary part of this? Just gonna boop. So that right there, ladies and gentlemen, is just our answer. It's pi over 2 times e minus 1. Thank you all so much for watching. I'm so happy to be doing some complex analysis again on the channel. This is truly one of my favorite subjects, and I will see you all in the next one. Thank you for watching. Bye!